Hello everyone, welcome back. Today we are going to break down a very important concept in biopharmaceutics and pharmacokinetics, the Michaelis-Menten equation, in the most easy and understandable way possible. So we'll first see this equation is also called as saturable metabolism or capacity limited metabolism or mixed order kinetics. Why? Because it tells us how the rate of drug metabolism depends on the concentration of the drug in the body. Here is the story. You can see when a drug enters your body, it finds an enzyme. Think of the enzyme as a lock and the drug as a key. They form a temporary complex like a handshake and then break apart, forming metabolite and leaving the enzyme free to repeat the process. This cycle goes on until all the drug is exhausted or gone. So here E is enzyme, D is drug or substrate. They form a complex and M is known as metabolite. Michaelis-Menten kinetics states that the rate of drug metabolism changes with change in the drug concentration. So here at high doses it follows zero order kinetics, and at moderate doses it follows mixed order, means sometimes zero or sometimes first order, and at low doses it follows first order. This point is known as Vmax and this point is known as Vmax by 2. This is Km. Km means Michaelis constant. Now comes the equation part. This right here shows how fast the drug is metabolized at any concentration. So the equation is V equals to minus dC by dt, or it is equals to Vmax C divided by Km plus C, where V is the rate of drug elimination of or metabolism. Minus dC by dt is equals to rate of decline in drug concentration with time. Vmax is the maximum rate of elimination. C is the drug concentration in plasma and Km is the Michaelis constant. Let's understand the types of kinetics. Depending on the concentration of the drug, the rate of metabolism changes. Let's break it down. First we have the first order kinetics. At low doses, at low concentration of substrate or drug. At low concentration, the drug follows first order kinetics. That means the higher the concentration, the faster it gets eliminated. More drug, faster removal, less drug, slower removal. And drug goes down exponentially, half-life stays the constant, and it is also called as linear kinetics. Now let's see the equation. This is the general equation where we saw back. So in the first order kinetics, concentration is very less. So when compared to Km is very less. So Km plus C, Km plus C we can write as Km only because concentration is negligible. So Km plus C we can write as Km. So in place of Km plus C we are writing only Km. So V equals to Vmax C divided by Km. This whole becomes K. So V equals to K into C we can write. After that, when we are removing equals to and K, there is proportionality. So V is directly proportional to C. It looks like linear kinetics. Now let's see the zero order kinetics at high concentration of substrate or drug. The definition is the drug is removed at a fixed amount per hour. So in zero order, the drug is removed at a constant rate. No matter how much drug is in the body, rate is constant, not affected by the drug levels. So a fixed amount of drug is removed. Example 10 mg per hour. It is seen when the enzymes or pathways get saturated. The half-life is not constant. It is also called as non-linear kinetics. Why it is risky? If you take more drugs, it is very dangerous and can lead to toxicity. Your body can't remove it faster, which leads to overdose or toxicity. Example, ethanol or phenytoin or aspirin at high doses. Now let's derive zero order equation with the help of the general equation V equals to V max C divided by Km plus C. So in this zero order, the concentration is very high and Km is negligible. So in place of Km plus C, we can write it as C only. So it becomes, this equation becomes V equals to V max C divided by C. C get cancelled, V equals to V max remains. Interpretation is the rate of metabolism becomes constant here, and this is zero order kinetics. Enzymes are fully saturated. They cannot work faster even with the more drug if you give. Here comes the interesting middle ground. Mixed order, medium concentration of substrate. When the concentration is close to Km. So Km plus C we can write it as 2C or 2Km. If you suppose it as C, then C plus C becomes 2C. Or if you suppose it as Km, then Km plus Km becomes 2Km. So our equation becomes V equals to V max C divided by Km plus C. In place of Km plus C, we can write it as 2C. Yes. So V equals to V max C divided by 2C. Okay. So after simplification, V equals to V max divided by 2 remains. So here the rate is the half of the V max. This is called as mixed order kinetics. Elimination is partly first order or partly zero order. Here is a summarized table for you to remember it. First we have the drug concentration, low, medium, high. So drug concentration is firstly we have low, then we have medium, then we have the high concentration of drug. Then approximation used is Km plus C is Km. Km plus C is equals to 2 Km or 2C. Here Km plus C is equals to C only. Then simplified V equation is V equals to V max C divided by Km. Here V equals to V max divided by 2. V equals to V max. Here it follows first order. Here it follows mixed order. Here it follows zero order kinetics. Now let's see how we calculate Km and Vmax using real data after IV bolus administration. So Km is the Michaelis constant and Vmax is the maximum velocity. Km tells us the concentration of the drug at which the metabolism rate is half of Vmax, while the Vmax is the maximum rate at which the enzyme can metabolize the drug. These parameters are estimated from plasma concentration versus time data after IV bolus administration. So our starting equation was V equals to Vmax C divided by Km plus C. So, and after integration of this equation and converting it to log base 10, we get log C naught, log C equals to log C naught minus V max T divided by 2.303 into Km, where we have the C is the plasma concentration at time t, C naught plasma concentration at time 0, T is the time after administration, Vmax is the maximum metabolism rate, Km is the Michaelis constant. Now if you look at this equation, see this equation, it is in the form of y equals to mx plus c. Okay, log c is the y axis, t is the x axis, slope is the minus Vmax divided by 2.303 and y-intercept is the log C naught. Now plot log of plasma concentration versus time graph. The terminal portion of the curve becomes straight. If you extend it back to 0 to time 0, you get the y-intercept log C naught. From the slope, you can find Km, and from the intercept, you can calculate C naught. Okay, log C on y-axis versus time axis, x-axis. Okay, these are the instructions to follow when you are plotting the graph. Then after that, we have to calculate Km and Vmax. Km equals to minus Vmax divided by slope 2.303. So once you find Km, use it again to calculate Vmax from the slope. Now here is the bonus point. At low plasma concentration, okay, so it means at very low levels of drug concentration, okay, when compared to Km, the drug concentration is very less. So we can simplify the equation even more simple way, which becomes log C equals to log C naught minus V max T divided by 2.303. We can also use this log C naught minus C equals to C naught minus C divided by 2.303. So from this data, Km can be calculated by rearranging the formula based on experimental values. So the next time someone tells you drug metabolism is simple, you know that it depends on the drug, the dose, the enzyme, and how saturated that enzymes get. Understanding this is crucial for drugs like phenytoin and theophylline because small increases in dose can lead to major toxicity. If you found this video helpful, share it with your friends and classmates and comment if you have any doubts. Till then, study hard and we'll meet in the next video. Thank you.